what will we not have in the circuits? What's something that we've been solving for, all this other shit, all the other ones we've been working, what won't be present?
Impedance? Yeah.
Impedance will still be present. Because, you know, so
true power.
That's right. True power, we won't have any, right?
Yeah, yeah.
And if we don't have true power, we're not going to have a power factor either, right?
Yeah.
Because, you know, power factor is the ratio between true power
and apparent power
to apparent power, right? All the power factor is showing the percentage of our total power that's actual usable power, right? So there's no resistance, there is zero usable power there, right? But there will be an impedance. The impedance formula just gets a hell of a lot easier in a series LC circuit. So we don't have this, right? So we're left with Z equals the square root of XL minus XC squared, right? Okay, we can go further here because the square root of a square is just that square, right? So in a series circuit, your impedance is just going to be simply XL minus XC. Or XC minus XL, whichever one, right? Remember, no negative fucking impedances. It's not possible, right? Okay, all good there? I mean, really, this the LC shit's easy because it takes that resistance out of it. So you don't have stuff that's 90 degrees out of phase now, right? You got rid of this part of our triangle. All we have left is this. You got your voltage, your induced voltage, your capacitive voltage, right? They're opposing each other. So when you want to figure out your total voltage, simple is that simple, right? Because they're just 180 degrees out of phase, completely opposing each other, so no need for square roots and all that nonsense, right? Alright, so we got a few circuits we're going to analyze. First off, does anyone know what the two lines above the inductor means?
The dielectric. No, that's the capacitor.
Two lines over the inductor symbol denotes that it's an iron core inductor. That's why when you get into transformers, so you'll often see it drawn like this because there's iron core in the transformer. But that is a lesson for another day. All right, we've got an inductor and capacitor in series connected to a source. 3 amps is flowing through this circuit.
Sorry, I can't help you with that on Apple Watch.
Alright, so got our inductor's got an inductive reactance of 80 ohms. Capacitor has capacitive reactance of 35 ohms. Alright, so we want to figure out what our total applied voltage is. Okay? So we're going to start off, let's see what our voltage drop is across each of these components. All right, we got 240 volts dropped across our inductor. Uh, 105 volts dropped across our capacitor. So for our total voltage at the source, it will be EL minus EC. So we have an applied voltage of 135 volts. All right, so if we was to draw this out vectorally, like they love for us to do, look something like that. All right, so we got, going up with our induced voltage. Our capacitive voltage is driving it down 105 volts. We'll meet in the middle at 135. I got that? Fairly easy concept here, right? Yeah. Just keep in mind that EL and EC are 180 degrees out of phase with each other. So they directly oppose each other. Okay? Alright, so we have got a 106 millihenry inductor connected to a 106 microfarad capacitor in series. Got 100 volt, 60 hertz source. We want to calculate what the total current is. All right, so what's our first step?
Change your henries and picofarads into resistance.
All right, well, henries and farads does not help us at all with Ohm's law, right? There's no ohms whatsoever up there. So anytime we see the funny letters, we need to get it in something that we can use, right?
Correct.
All right, so got 40 ohms of inductive reactance and 25 ohms of capacitive reactance. All right, so we need to combine these two, right? Alright, so we have a impedance of 15 ohms. So now we can calculate our current. Right, so we have a total current of 6.67 amps. Now that we know our current, we can calculate the voltage drop across each component.
So you can't take the inductive reactance or the capacitive reactance individually and get the amperage like that. You can't take just one of them and get
No, because it's a series circuit, so it's going to be the same.
Yeah.
The current's going to stay the same all throughout that circuit.
Yeah.
Alright, then after we get the voltage drop across the components, we can calculate the total voltage and check it with our circuit. Alright, so that checks out. All right, you have any questions? Now go with series LC circuits.
What's that?
I mean, it is. You know, like I say, you don't have to worry about the fucking square root and Pythagorean theorem and all that shit. It's just plus and minus, right?
Getting rid of resistance cuts down on most of it.
It does. It does. I mean, this is all the same shit y'all been doing, just a little bit simpler. Huh?
I got a question. Why did you throw the iron ore symbol in there on this one?
Yeah, just to show it to you.
So
It's not, no, it doesn't affect anything. You'll see it sometimes in the homework. It might have it on there.
okay, so you're just letting us know that the curveball was coming on the homework.
Yeah, I mean, yeah, that's. I mean, all you need to be worried about is the humps. Don't worry about the bars over it. Just worry about the humps, right? That's all that fucking matters. You know, it can have whatever the fuck it wants to above it, but at the end of the day, it's still just a fucking inductor. No matter what the damn core is, it's still a fucking inductor. Now, getting deep into it, you know, how we talked a little bit about that long, drawn-out, stupid-ass formula to calculate the inductance of an inductor without knowing. We don't need to know that shit. This is just something that you'll see, especially as we get into transformers, because there'll be a lot more iron core transformers in there, and you'll be wondering what that is. That's not necessarily just a transformer thing. Right?
Second question. Are we going to be able to apply the powered method that we used last week to this stuff?
What power method?
Apply, like the parent, like
there's not. I mean, there is apparent power, but there's not.
No, I'm sorry. I might not be using the right term, but it was like approximated whatever.
Oh, the assumed voltage shit.
Yeah.
Yeah, I mean, it will, but it's the same shit. I mean, it really is. Which that would be only on a parallel circuit that you could use the assumed voltage method, because it's going to stay the same throughout the circuit, right? Yeah, you can use that, absolutely. If you're looking for impedance, you can use that, but only on parallel circuits. Don't try to do assumed voltage on a series circuit, because it will not work. I mean, it stands to reason you could use a assumed current. I've never heard that shit, never seen it, but it stands to reason that you could on a series circuit. But, I mean, it's very few steps. When you just have an LC circuit, you know, it's 3 steps and you've got your impedance, right?
That's all theoretical. That circuit, right? LC circuit. I mean, you will have resistance.
Yeah, there's always going to be some. I mean, just in this.
Yeah.
In your wire, there's resistance there. You know, just for the sake of teaching, maybe. In theory.
Yeah.
You know, this is just teaching you the relationships and all that shit again. But yeah, that you'll never find a circuit ever that has 0 resistance, right? Because what happens when you have 0 resistance?
It's perfect.
Exactly, Alan. Boom. 0 resistance is a direct short, right? More or less. It's taking 2 wires and putting them together, right?
Yeah.
Right. So yeah, you will never see this shit in anything that we're doing, because it's impossible. You know, unless they start the Tesla method of wireless power distribution,
Bare copper.
never going to see, right? So now that you are all experts in the series LCs, let's go to parallel LC. Now this motherfucker was just right and good. There we go. Alright, so we have a 80 ohm inductor and a 35 ohm capacitor connected in parallel with a 135 volt source. We want to find our impedance. What's our first step?
Find the current.
Absolute. Alright, so how do we do IT?
Subtraction.
Absolutely. Alright, so we got a total current of 2.17 amps. Now we can calculate our impedance. So, what type of power will be present here?
And reactive.
Reactive. I mean, technically not apparent power, even though the way that you would calculate the power in this is just ET times IT, right? It's technically not apparent power because apparent power is our hypotenuse, right? We just got this leg because we don't have the other leg.
We still got volt amps though.
No, it will not be measured in volt amps at all. It's 100% VARs.
Okay.
Because it's all reactive. I mean, technically, yes, the total power of the circuit, which is, and everything else has been our apparent power. But the total power in this one can only be VARs because it's all we got. Right? Y'all got that? same thing. We want to find our impedance for the circuit. What's our first step, Cam?
Oh, yeah, fine.
Alright, so first off, is this a more capacitive or more inductive?
Capacitive.
Why is it more capacitive?
Because it's got more resistance to it.
No, I mean our resistance,
It's got more.
our opposition, there's more opposition on the inductor side.
It's got more amperage.
It's got
Yeah.
more current.
Yeah.
Alright, so in a series circuit, whichever component's got the largest reactance value, you
Is
know,
what takes charge.
that it's going to be, you know, if your inductor's got more reactance than the capacitor, it's going to be an inductive circuit, right? Opposite on parallels. For one, you're looking at current, and two, it's going to be the smallest one because there's going to be more current flow here than right here. I got that? There's a lot of questions I know, like on the craft cert, about is the following circuit capacitive or inductive? You know, simple circuit, it's easy once you get that in your head that in series, if it's the bigger one, that's what it is. In parallel, the smaller one is what it is. Okay,
Here's
so
what I found.
Oh, today.
eavesdropping, bitch. So yeah, make you a note there because you'll definitely say that shit again because they love those questions. All right, so we got IL and IC. We can get our total current. All right, we got a total current flow of 1.5 amps. And an impedance of 66.67 ohms. All right, so y'all got this. Any questions, confusion, comments, cuss words? Fuck. What are we talking about?
And this is just going to be reactive, or voltance reactive as well. On
Yeah,
the
there's no
reactive power.
resistance. No resistance. I mean, so, you know, with these, so let's say there was a resistor in here, right? You would still use this number to calculate your bars, right? You know, because you're going to take your reactive current. Remember when we did the IX? It's all, in an LC circuit, that's all we're doing is IX, right? All right, I got all this. All right, now we're going to go back and talk about resonant frequency. Garrett, what is resonant frequency?
Something to do with AC theory. Something. And why? Resonant theory. Wait, could you read the question again?
Resonant frequency. Not resident, resonant.
Resonant? Not resonant, like residue resonant?
No, RESONANT. Resonant.
You spell the word one more time and use it in a sentence.
RESONANT. Garrett, tell me what the fuck resonant frequency is. How's that?
I'll use my mulligan.
Huh?
You use it in like a useful sentence.
Well, if I use it in a useful sentence,
What kind of sentence would you use that in?
the resonant frequency of the previous circuit is 22 hertz. And that's very helpful.
Okay, then something to do with the finding my some kind of equation or theory to find my hertz then, right? Whenever you're not
What is that? What is that equation? I've given it to you.
Isn't it
Bullshit.
FR equals 1 over 2 pi square root of
Fuck 2 pi. No.
FC.
Is there not a different one? I've got that wrote down somewhere. I remember it's in my notepad here.
But what does that mean? What does the resonant frequency mean?
Take the two
It's
reactors.
the frequency at which
Inductive reactance and capacitive reactance are equal in a circuit.
you
Look,
cheat
you got a
ass.
fucking book. That's cheating. Oh, we done. That's it.
Resonant frequency is where XL equals XC. Huh? Where your reactances equal each other. And if that happens, they completely cancel each other out. Right? Right? So, in an LC circuit, series LC circuit, well, RLC, sorry. Alright, so, if the circuit is at resonance, so its resonant frequency, what is our impedance then?
It's just going to be Z equals R.
Absolutely, because these two cats are canceling each other out, right? Okay.
Right.
So we don't have our we're back to LC circuit, right? What happens to our impedance at resonance?
There's no impedance.
Zero. They're canceling each other out, right? Okay, it's in a RLC circuit, resonance is what we all strive for, right? Why is that? Why do we want to try to achieve the resonant frequency with every circuit?
More efficient?
Well, I mean, it's as efficient as you can possibly get,
Yeah.
right? So, you know, if you got a RLC circuit at resonance, your power factor, which is R over Z, right? So in this equation, Z equals R, right? So what's anything divided by itself?
Itself.
So it's perfect frequency. I mean, perfect
Right.
power factor.
You've got a power factor of 1 or 100%. And it's a perfect circuit. You don't have any waste. Every single volt amp, watt, everything that's generated by this circuit is usable power. Every bit of it. So that's what we want. You know, we have all this reactive power. That's what fucks everything up. You know, with getting phase angles of, 90 or 80 something degrees that is a shit power factor, right? Because we got our long horizontal line. If we have a long reactive line with a lot of reactive power, this angle here gets bigger and bigger, right? Or even if it's a short resistance and super long up here, hell, it's you're getting closer and closer to 90 degrees there, right?
Closer to becoming in sync.
And we don't want that, because none of the shit up here on this axis is useful, right? Our resistive current and all is down here. This is all the usable shit. This up here is not. You don't want this shit at all. And I think maybe the next level of AC we get into like power factor correction. Now, I spoke a little bit about that before, right? Or did I imagine it?
That's why I was wondering how they do that, like Facebook with those inductors or with the capacitors,
At a place like Facebook, right? A lot of motors, fan motors, a lot of servers, a lot of LED lighting, fluorescent lighting, all that shit. All that is inductive loads.
They take the hertz. They try to get the hertz resonant frequency with the VFDs.
No, you'll try to achieve resonant frequency like on separate motors, not like a plant-wide thing. If you're doing a plant-wide power factor correction, it's done with capacitor banks. So inductors are no good for us. It throws everything out of sync. Anything like I said with motors, transformers, all that shit's inductive loads. So we know that inductors and capacitors run 180 degrees out of phase. So if you're super high with inductors, those capacitors in there and start bringing it down until you get to a appropriate power factor. Not only is it efficient as far as like the power bill, you actually places will get fined if their power factor drops to a certain point. They start getting fined until they get it corrected. And that's some of the problems we go through is you need to drop the inductance down a certain amount. How many capacitor banks will it take to do it? The capacitor banks cost X amount. How much will it take? How long will it take for them to make their money back? Type thing, right? All right. So resonant frequency. So if we take the circuit we just did with the 80 ohm inductor, or whatever the fucking call it, 40 ohm inductor and the 25 ohm capacitor. We take those and calculate our resonant frequency.